Okay, welcome everybody. Thanks for joining us, even though it's already 5 p.m. Today we're going to talk about how we created the Games as a Service in Azure and what we learned about that. And before we go into more details what we actually did, I want to introduce ourselves and introduce our company. So I'm Kalle Hitola. I'm the CTO and co-founder of Next Games, and with me is
Remo Kallio, I'm Technical Director in the Backend Services.
So Next Games is a free-to-play mobile game company. We provide games for Android and iOS. We were founded in 2013. We became a part of the Bespoke program of Microsoft pretty early on. In 2015, we launched our first title, which is the Compass Point West. It's basically a battle builder. Many of you might know Clash of Clans as a game. So it's basically the same kind of a game, but with a twist of card collection and Western theme. In October of 2015, we launched our major title, which is The Walking Dead: No Man's Land. It's based on the TV series. I don't know how many of you actually know this TV series. How many of you actually watch the TV series? Excellent. We have fans here. So that was big success. So when we launched that in October, we went to the #1 on Apple iTunes Store in downloads. So we bypassed applications like Facebook, which is usually the #1 there. Great achievement for a young company. And just a few months ago, we actually went public. We done a IPO. So we are the first Finnish gaming company to actually do an IPO, even though there's like bigger names in Finland that you probably know, like Rovio, who's responsible for Angry Birds, or Supercell, who's responsible for the Clash of Clans and other titles. But our biggest game is definitely The Walking Dead: No Man's Land. It's been now downloaded by 16 million times, pretty much 50-50 on Android and iOS. We send extensive amount of data out of that, so we generate around 120 gigabytes worth of analytics data each day, which is quite a nice portion of data to work with. We use a lot of Cosmos DB, and for that we hit around 11,000 requests per second. And each day, players approximately kill 43 million walkers. So, you know, if the whole US was turned into walkers, we could jump through that in a week or something. And The Walking Dead is actually one of the first mobile games in the world that is actually so tightly coupled with the TV show. So every Sunday when the TV show is running, after the show, the next Monday, we basically can upload new content into the game, which relates to that episode that people saw just the day before. So if they're in the previous episode, the people were in some environment, or new character was introduced, or new items were introduced, new weapons or something like that, we can bring those into the game straight away. So that's a pretty neat feature for all the fans. So let's drop into a bit more to technical stuff. So here you can see our sort of like a high-level architecture. What are our building blocks which we build our backend system onto? So we have our client. We used Unity 3D as our client engine, and we build our clients on iOS and Android. We support phones and tablets. For load balancing, we use Traffic Manager from Azure. And also cloud services play a part in there, because all our compute is happening on cloud services. So the front servers handle all our game logic hosting. They'll load the players' states. We have analytics servers that does the dispatching of analytics events. We have the controller that handles all the internal dispatching of information between the servers. So we basically created our own little service bus to handle communication between servers. We have our own content delivery system that uses third-party CDN and Azure Media Services. So for example, with Azure Media Services, when we can provide sneak previews from upcoming episodes or exclusive content from the TV show. We use we have a leaderboard service that handles all our high scores, like if the guilds are battling or individual people want to see where they are in high scores, we can have multiple different high scores for country-specific or region-specific or global. And we also have a very extensive dashboard that we use for our game management. So we have built this management tool where our support and live operations can actually put in new content or fix a problem with a specific player has. And all that is tied together, the dashboard, with the global authentication. We use web apps there, so we use that in order to authenticate all the users into our dashboard. And then we can use other single sign-on services there, like Google Authentication or Microsoft Authentication. And also, we use external monitoring tools. We use Datadog to monitor all our servers and what's going on in there. It's a great service in that sense. We use PagerDuty to be able to alarm our server people if something goes wrong. We have a status page IO page set up, so we can actually show if we're working on some problem that people don't get scared what's going on, and the information flow is guaranteed. And we have a log entries in order to get our logs all in the same place. And on the data storage level, for player data, we use Azure Blob Storage. So that's a very great way of storing files. Works very well for us. And we use Cosmos DB in order to store the metadata of the players. So we can actually query specific properties of the player and the player state. Cosmos DB also handles all our leaderboards. So quite recently, Document DB introduced the ability to actually sort stuff within their queries that have made our life a whole lot easier. We use Cosmos DB to have our in-app purchase ledger and validation. Azure Blob Storage is used for content. Social services use Azure Table Storage. That's the final place. We will still use Azure Table Storage, but it's really good for when you wanna have sort of queued messages that are in a certain order and persist them for a long time. And for analytics, as I mentioned probably earlier, we use Event Hub. So what we have actually built is a very generic platform. We aimed for creating one platform for multiple titles. We wanted to make sure that we can share all the features between different titles. So if we develop one feature on within the backend, it will be available for the other titles also. So when we introduced, for example, in the Compass Point West, we introduced guild systems. Right away, that was available for the Walking Dead as a service on our backend. Obviously, this makes our time to market way faster. So with this kind of approach, we don't have to always rewrite these same kind of things like storing the player or creating high scores or whatever for each title. We can just reuse what we already done. And actually, the server doesn't even care what kind of game is running. As long as the game just implements our simple sort of interfaces to us, to the server, the game is just a place where to push some commands into. But the logic that we run there doesn't really matter what it is. So when we started our company and started to think about what kind of solution we want to create, we started off with 4 pretty basic design principles. Firstly, we always wanted to use all the possible pre-made services that are available there. We wanted to stray away from this not invented here problem. So with that, we were able to actually focus in the game instead of focusing into creating technology itself. I think probably Microsoft is way better in creating technology than we are. We're pretty good in games. One thing that we wanted to do is we never want to trust the client, so we want to be able to compute everything on the server side. Because if we wouldn't trust the client, pretty soon the players would start cheat against each other, and that would ruin their experience. We wanted to start thinking scaling first. So it's really hard to get something first work and then try to make it scale. So we want to do another way around. We want to first think how you scale and then make it work. And as games these times are live, we want to remember live operations, so how we can continue to evolve those games. I'm going to go through each of one of these and sort of like what do we do, how do we solve these design principles and what we learned actually while using those. So existing services, Unity 3D, that was sort of a no-brainer. It uses C# for scripting. What else could you ask, basically? We can then run the same logic on the server and on the client. We could share the same code between these two different environments. That was one of the key things why we choose Azure in the first place. We want to be able to run C# natively. 2013, there was no such thing as .NET Core. Other option would have been running the code on top of Mono, but then again, performance wouldn't be optimal. Unity 3D is really easy to pick up and understand, so it's relatively easy to recruit people, and people get really fast into the project. So it doesn't take for a new game programmer like multiple months to just start understand how our game engine would work. They just basically can come in and start on day one to program against it. And it's basically an industry standard these days. Like if you look at the small mobile game companies, they all are starting off with Unity. And as I mentioned earlier, we choose to use these other existing services like log entries. We created our own centralized log system. And pretty soon our game team or support people started to ask like all sorts of features for gathering those logs. Could we query them by time? Could we group them? Could we find some special value out of there? Could we set up alarms out of certain events that happen on the log? So it became like a never-ending list of feature requests. So I figured like there must be a service for it. So we found log entries and we'd be very happy with it. Same thing, we were monitoring our servers. We wanted to make sure that we can actually time all the functions that happen within the servers and make sure that we know exactly what are the functions of the servers that eat most of the resources. With Datadog, we were actually able to time each and every function call that happens within the server, so we could really clearly see what's consuming most of our CPU or memory and things like that. And that's probably these days available to Azure app sites, but 2013, those kind of things weren't just available, so we need to make a decision then. And PagerDuty has been a lifesaver for us. Many of our server team people know how well that works because they get a peeping sound on their phones during nights through that system. And then one of the services that we used to support our player support is HelpShift. That's actually like a whole ecosystem, how to talk with the players, how to handle ticketing and things like that. We didn't want to actually start working and creating our own system for ticketing. There's a better system for that. So, the deterministic model, never trust the client. As I mentioned, one of our principles was that we should never trust the client, never. So what is a model? So basically, it's the game logic. What we do, we run the game logic on the server and on the client at the same time. So it's really hard for the players to cheat on. Whatever you run on the client, you execute firstly there and then on the server. Actually, you can see it even better here. So to explain it more in detail, you can see here, if we have a client that first connects to the server, so it makes an HTTP call, and then we return an address for it. And we use signal R in order to keep on those connections. And through signal R, we actually use WebSockets to establish that connection. Now, once that is done, the server will load the game logic on the server side of things. It will run the player state. We keep that in memory during the gaming session of the player. And don't unload it until we notice that the player doesn't actually send any more of the commands. Now, in this stage, the server returns the game state back to the client. So now we have the same logic running on both ends. in between is actually JSON that we deliver back to the client, and it will start the same logic. And this is now deterministic logic. So whatever happens on the client side should end up with the same results on the server side. And whenever the player actually does any interactions within the game, we create a command that we send into the game logic, and it will be executed on that game logic. That will be happening asynchronously, so we can keep on executing those, even though there will be other commands waiting to be sent through the wire to the server. So the experience for the player is still smooth. We don't have to wait for answer from the logic before we execute other commands or answers from the server in that matter. So then we send that over the wire with JSON format to the server, which will then execute the same command, and it should come up with the same results if everything is in sync. If you have, for example, if you're trying to collect resources out of a building within your game, you have X amount of resources there. Within the command, we don't actually send the values or anything like that. We just say collect this building, and you should be getting the same amount of resources on both ends, on the client and also on the server. If then the player tries to use, for example, on the client more resources that are available, we would notice that when we execute using of those resources on the server side, and resources wouldn't be available. Once the execution happens on the server side, we will return a boolean basically, saying that if it went through well or not. If it fails, we will actually just reload the state of the game back from the server to the client. So the client would just see a reload of the game, like the loading screen will show up quickly, and then they can continue playing the game. And once the session ends, the player will be stored back into the storage, to the Azure Blob Storage and Document DB. Now Remo is going to actually show you in practice how this works.
So let's make the day's first demo effect probably. So I will check my connections. Yes. So model, what model is? In a nutshell, model is context of data. And in C# world, we can call this as a class. Class have properties that you want to have, like amount of diamonds, amount of gold you have. And then you have commands that is actually a function in that class, but extracted away in the manner of putting them as a JSON format to replay them if needed. So here I have one nifty command that actually is really simple. Hopefully no magic thing happens here. So the command is, I want to cut vegetations from the camp itself. So I want to modify this command. I will add one line of log error here. So I will tell my grass is now cleaned. I will save that. I will open my Unity. It's probably built that. And I want to now go to the server side. I will notify that file is changed. I have the same stuff here in the Visual Studio. Probably want to put a little bit bigger. Little bit bigger, not that much. So I have the same one here, the line, in the server side in Visual Studio. And now I will try to close this one. Yes. So I will start my server. And this is a local build, so let's see if everything works. And at the same time, it builds in the client side. So I have a remote desktop in the server side and the client side here. I made change in my client side to add this model debug here. I could debug code here in the client, but because this is Mac and Visual Studio latest update broke this, so bear with me, I can show this same effect anyway. So server is up and running. I can check my logs that it actually is. Yeah, it is. So I'm happy with it. I will try to connect. And then we probably break something. It's coming. There it is. So let's create a logs. This is debug build, so there's a shitload of stuff happening. But in the end, what I need to do is I want to clean this junk away. I will clean this. Everything's OK. I have my small log here that clean my grass as I typed in. I go in the server side. I have the same thing. I have the same log here telling me that I want to clean this up. Of course, at the same time, I can put debug here, I can put breakpoints, so I can debug, or nowadays even Visual Studio provides you that you can actually collect data in the real-time production environment, so you can see what actually happens here in production environment. So this is kind of cool to have. And this is the exact same C# file that the client is using in Unity side, and client is using, that we are using the server side during this time. And this is the actual model running in the server, keeping us happy.
Okay, so why did we go through all that trouble? Firstly, we don't have to write a separate validation code. So often how the games are done is that you write them in C++, then you have, for example, Java or PHP or whatever as your server backend. And once you introduce a new feature on the client side of things, you will then need to write the same feature logic on the server side. So basically you need two resources. You need a client programmer to write it on a client, and you need a server programmer to write the exact same thing again on the server side. And hopefully they will actually execute even the same logic. We don't need to do that because we're using the exact same code. Makes our lives a lot more easier. It's more rapid to test. It's way more easier to deploy because you're deploying the same code that you're doing. That also makes the game programmers responsible for their server-side logic, so they share the pain of the server programmers. And this also enables us to do asynchronous execution with queue. So what we do is we send them in queue while they're on the client side, all the commands. So we can just pump a lot of commands there while we're waiting for one of the commands coming back. And once it comes back, we just batch all the commands into one big message and send it on the server. So if there's a large round trip time to wait for, we can execute more commands in a shorter time. And if failure happens, we just reload the game state from the server side. This also enables us to actually hotfix stuff on the server side. So whenever we find a problem within our logic, we can easily change the whole game model on the server. So we can do fixes that solve problems during the loading of the player, or we can change the execution of the command on the server side without actually needing to deploy the client. And deploying client could take days because we're talking about Android and iOS clients, so they have a review process that we need to go through. It used to be really bad on Apple side, like taking 2 weeks or something like that. And you can imagine if we introduce a really bad bug and are not able to solve that within a few weeks, we'll be in great trouble. But luckily, we can often do these changes on the server side. So we can solve these in a way that maybe there's a faulty command that will cause once your client to reload, but afterwards it will work just fine, or we can solve it when the player is loading. And this enables us not to trust the client at all. So the server is always the authoritative party of this system. And the client basically first does all the actions, and then those are replicated on the shadow model on the server side. Of course, doing these kind of things doesn't come without any cost, so we learned also something. So it turns out when we were doing this, like Mono and actual C# don't do all the things exactly the same way, even though they both obey the same certificates and same rules. There's some slight little differences. Sorting wasn't obviously working. They execute different kind of sorting mechanisms. And surprisingly enough, if you try to send floats over the wire in JSON, you can imagine what happens. You get different results. But it's really hard to debug sometimes. But we did solve those, and Remo is now going to show how did we solve, firstly, the sorting, and then how we manage with the floats.
So sorting, it's easy to think that you have an array of something and you sort them by name, by a number, by whatever the comparer is that you get same result whatever the device or whatever your language is. Turns out that is not the case because there's differences. So in many cases, when we use .NET in our system, it's going to be server-side. It will be Windows full-blown .NET, so everything is nice and needy. So in Windows, I have a snippet here that is actual implementation. So in the list sort that we use, it uses underline the array sort that is basically static function that gives you all the items and everything, so simple. But it's implemented in totally managed C#. So it's totally managed code. Everything is in C#. And here's the snippet, how it actually does. It tries to do the mediation, create with blah, blah, blah. So optimizes that if you have something already sort, it basically skips that. This is all good. Everything is fine. It works almost every time, 99% of times, and also works for us. But then again, when you will have more devices, different kind of devices, you will notice that there's a kind of issues. And quick sort, as its name says, it's going to be quick sort that actually has some limitations, like it will basically fake things. And then we switch to the mono because we use Android and iOS device. In the end, it's the same thing. They use array sort, but they use C++ implementation of sort, quick sort. So we already have one problem that we don't actually anymore be in the managed environment, and now we use native code, which is already something different can happen. And also it relays to platform implementation. So it's platform, when Windows side did one thing, iOS did one thing, Android basically just did something. The Android version is kind of crappy. And also the problem is that if platform update comes in, so let's say iOS gets new version, it can change something quick sort, even though it's quick sort, so it should be quick sort, but I don't know what happened, something is broken. And okay, there's of course the floats, so if you try to sort by the float, you have the same problem as floating point problem that we'll actually show you in next. But why it's good? Why quick sort is that good that actually the core implementation of .NET is using that? And there's a couple of sentences I have heard, and I think like this scales your data. Yeah, it scales probably, but it's still a sort. I think this is the last one I heard a couple of years ago, that it's actually preventing you to do something that actually crashes your server. It's this kind of weird way to say something, but okay, it does that. It's a quick sort, so it basically saves you CPU time. So it's fast. And this is our stable, noble version. So this is the actual implementation happening, and then we have our implementation. This is not quick. There's no optimizations. It just lists things using comparison to actual list the hardest way, so going through all the items all the time. And that's totally fine, because in the game modes, you don't have millions of data. You probably don't want to have millions of rows of stuff in your array, or you don't have millions of bytes array to do. So it works in the game, so you have less than 1,000 items, which is totally fine, so it's fast enough. CPUs in your mobile phones nowadays are more power than most of the desktop devices, so it's good enough. And of course, there's always this nice little cheap clone Android devices from the Chinese market that actually the GPU is so bad that you will hit some performance problems. But in the end, if the CPU is that bad, probably the game is not even running, so we kind of can skip that. So quicksort is scalable, even though we don't use the quick one.
Fixed point.
Fixed point. Okay, yeah, so floats. So float is number, floating point. Easy to think that we have a point in number, so it floats. It's kind of already telling you that it's not deterministic, so there's a problem when you use that in server that is actual high-end server. And I think this is a good one I heard in that, like, if you treat your machine that is a cold-plated CPU in controlled environment, and then you take your iPhone from your pocket, it's kind of different CPU environment already. So there's a standard. There's an IEE standard that actually tells us how floating points should work. But what happens to the standards? No one actually, it's standardish. So it's there, but kind of. So hardware and also software, but AMD is doing some crazy multiply add instructions at the CPU level. So that already breaks the optimization. It breaks basically the floating point stuff. And also, this is the old debate. that you can define in Intel processor, yes, I want to use only 64 bits, but in the end it's still 80 bits. So there's already, in the desktop level, we have two kinds of floats. What it actually means I try to have this nice little example here, that if you have one floating point that you want to read only like two numbers, in server side you will have 1.5 here, because if you do rounding by two numbers, it goes to 1.5. In game, you are some slot in the game, in tile 1, so it's totally fine. But in the client side, you have a crappy CPU that only sees, let's say, 2 or 3 numbers. If you round that, you get 1.4. So there's something wrong with the floating point in that sense, that you get different numbers. Those numbers don't, I just type them in, but the idea is the same. So that means that in the client side, you might be in the edge of the hole, because you're 1.4, and in the server side, you're 1.5, so you're basically already inside the hole. And so it's really hard to move away from that point. So that's the issue that we have. How to actually implement the C# side? You can create this long value, and long value is now not pointable value, so that means that you don't need to have this worrying floating point anymore. And it's relatively simple to do. This is simple example. Pick your scale, how you want to scale your number based on your crappiest CPU you want to scale. And then you implement all those nice C# features once. And when you store your model, instead of using float, use this fixed point. And now you have a number that actually you have a number that has that much value after the point that you care. And it's deterministic all the way in all the devices that you want to support. So there's many lines, but trust me, do it once or download a NuGet package and you are much happier with it. Because this problem all basically comes into your play when you're going production ready. Before that, you will not see that, probably.
Okay, let's continue. Then one of the principles that we had was this having the scaling in your mind all the time. So how do we actually do our connectivity and scaling? So I'll quickly go through how we handle our connectivity and how do we actually scale. So firstly, when the user connects from their device, we first send a request to Traffic Manager. Azure Traffic Manager is DNS-based load balancing. Probably many of you are familiar with. It's relatively old technology from Azure stack. But that will then direct the request to one of the cloud services that we have for our front servers. So we have plenty of those. It can range depending on the game, but we can have 3 or we can have 20, depending on the situation. And we can also use Traffic Manager to do sort of rolling updates. So we can drop some of the front servers off the circulation from Traffic Manager and then upload new version of the cloud services while they're off the circulation and then change the code there. Well, anyway, once the request goes to the front cloud services, that cloud service will do a second level of load balancing, because cloud service itself is basically just set of managed VMs that sit behind a load balancer. That load balancer will randomly basically select one of those instances and distribute the load between all the instances that are underneath that cloud service. Once that request hits that certain instance, we will then reconstruct an address for that instance. Basically, it's the name of the cloud service and our own domain name, plus a port number, which is an instance-specific port number. We will then return that back to our client and use that address to establish this single R connection back to this very specific instance. Why do we do this? It's because if the connection happens to drop, if the player moves from Wi-Fi connection to cellular connection with their mobile device, we want to make sure that they hit back on the same instance, because the way we store the player, it's in the memory, so we want to keep it in memory, because that's the cheapest way of actually keeping the player available, is to keep it in memory. Otherwise, we would need to store it on some sort of middle caching system like Redis or something like that, but that would always need us to serialize the model, and we use JSON as our serialization. So as I mentioned, we cache a lot. We keep the players in memory. And that's single-handedly the fastest way of accessing those players when we want to fetch the player for example, a command to be executed. And we keep the memory as long as they send some sort of commands. We have time to leave there, and if they don't send any commands, we notice that, and then we start offloading that player from the memory of that instance. That also brings us a little problem that we are also CPU bound. Because what we do, we have a really large JSON files basically represent the state of the player. And the biggest one of those can be up to 4 megabytes. You can imagine that it's pretty much of memory, but it also eats a lot of CPU when you serialize and deserialize that kind of complex JSON object. When we are storing the JSON, partition is our friend for scaling. Basically, on one storage account, you have the limit of doing 20,000 requests per second. That's limited into 2,000 per container on blob storage. So you need to make sure that you have a specific container for each of your player that you store, which we have. So you can come up with the full potential of 20,000 requests per second per storage account. But our aim was, when we started to build this, we were almost aiming for at least 1 million concurrent users. So we were sure that we were able to handle the traffic, because there was no way of telling how many players we will get on the day that we launch the game and we start marketing that game while the premiere of The Walking Dead for that season was going on. So easy way to scale it beyond the 20,000 is actually just starting creating more storage accounts. So we created 96 storage accounts, which is sort of like bending the rules, but it worked pretty well. And the other thing that is crucial for us to be able to scale is our social features. So you want to be able to send messages between players and groups and guilds. And to us, our social model, way we build it, is that it doesn't actually care, as we don't on any aspect, like the player model. It doesn't really care what the commands hold. In the end of the day, for the server, there's just strings that we move along and give them to the model to execute, or JSON representation of those commands. And it's the same thing with our social features. For us, the social messages that we send, is either if it's for a member to be promoted in a guild, or giving gifts for your guild members, or sending a chat message, they're all just social commands. And the way we send those between the players is that we actually first send them through normal player command. So that's executed against the deterministic model of the player. And once that is validated and the model sees that it's just fine to send it forward, we actually call our social services on the front server. And that social service will then send that message to the social server that we have plenty of, to that social server where the player is subscribed to. So it'll know which server to send that message to. We then take that message, we store it in order to table storage, so we can actually create sort of a transactional log that we can play back if necessary. And if the model wants to, if it feels like it's been doing something so important that it should create a snapshot, in this moment it can actually create a snapshot. But we're not running the model itself in the social servers. The social server is just handling the transactional queue and making sure that everybody gets the messages in the same order. Because our social models are also deterministic. So as long as they get the messages in right order, everything should be fine. So then the social server will start to distribute these messages back to the front servers that hold the clients that are member of that group where the social message belongs to. Let's say it's a guild, so they have like 4 members in that guild. So those messages will get on the front servers, and the front servers will do the execution against the social model. And once the social model thinks that this execution was fine, it will then decide if it wants to actually inform this information back to the client. So it's up to the game programmers actually to figure out if they want to send some information back to the client or not. This brings a lot of power to the game programmers out of the server programmers' hands. So basically the server just provides means, and then the game programmers can figure out how they want to handle their social features. And you can imagine this is a very valuable feature for when you're creating new titles. So you're not tied to a certain way of handling your social aspects or social services within the game. So what did we learn about scaling? Testing, that's really hard. Load testing is terribly, terribly hard. We used Visual Studio Online because they had some really nice load testing features available. So what we did, we basically created a unit test that we distributed through Visual Studio Online. And the unit test was basically a single R client that we recorded the commands of a normal gameplay session. We simulated to the server, it looks like any client connecting with simulated commands that were recorded from actual gameplay. Then we would run tons of those in parallel inside the unit test. So one unit test would itself, from one agent, would try to create, let's say, 1,000 or 2,000 clients. And then we let Visual Studio Online to run those in parallel. And then we saw how that system crashed itself. We just ended up like we were trying to put millions and millions of clients up and running, but unfortunately the Visual Studio Online testing system wasn't quite up to that task yet during that time. I think they're better these days, but that was a few years back. So we ended up deploying our own agents. So that's a good way of doing that. It's not actually that hard to create your own test agents and deploy those on the VMs. So it's relatively simple to do. Also, we learned, as we've been talking about a lot, is like we were using JSON. Don't do it. Just don't. The argument you hear often is people are saying like, but JSON is so nice when I'm debugging. But as I wrote there, it's basically just saying I'm too lazy to write a tool so I could actually peek in what's going on in my binary format. And the other thing that you often hear is that, okay, we'll do the switch once we go production. Yeah, right. How many of you have done that switch and made that promise? I can imagine that people, I'm seeing guilty faces in the audience. Nobody does that. That's just lying to yourself. It will never happen, never. Or I yet to haven't heard a situation where that has happened. So investigate something like flat buffers or any other decent binary format to use. We will also in future, so we will do the change. And you can see the truth from the previous slide, how that's going to happen. Anyway, okay. As I mentioned, like the fourth principle for our design is the live operations. So what does this actually mean? Well, the modern games are very different from the sort of old-day console games, or the model of the model that the console games have. Basically, console games usually it's you give $50, you get a disc. Right about there, the developer starts to be really happy. That's it. They will basically take your money and run. You're lucky if they produce a DLC. If there's a bad enough bug, they will produce a patch, obviously. But that's it. The game itself doesn't evolve. It doesn't probably change that much. It's pretty static, unless there's some other kind of business model behind it. These days, games are services. They live for years and years and years on. They keep on evolving. We keep on introducing new features in the game all the time. When we launched The Walking Dead, we didn't have player versus player at all in the game. Probably a few players were a bit disappointed. But within a few months, we introduced that as a new feature into our game. We also introduced other aspects, like new features in how to play your guilds and things like that. And the game keeps on growing. We keep on introducing new content into the games. We Last summer, we introduced the characters from the TV show to be playable within the game. And every week, we introduce new weapons, new characters, new environments. So it's continuously growing. These days, the games needs to feel that they are alive. So players want that they feel like there's somebody else working on the game, presenting new events, presenting new stuff to do each and every day, each and every week. It needs to feel alive. So in order to do that, we needed to create a good content delivery system. And what we have done is actually we have our own dashboard where we can create segments of the players, and we can, for certain segments, we can create certain content that we can deliver. You can see that those contents could easily be, for example, a bundle that they can purchase through in-app purchases, or it could be a special event to only focus certain group of players, or it just could be as easy as a news banner or other event or anything like that. And the way we have done that is that we have a dashboard that first publishes everything on a controller, which is basically this service bus that we have. And then can distribute then the data over to Azure Media Services if we were talking about video delivery. So we show sneak previews and exclusive content of the TV series on The Walking Dead. Or we deliver that to CDN so the clients can actually download that and present new content for the players. And if we need that same content to be available on the server side, because as I was telling, we validate everything on the server side, try to run the same logic. So if we provide some new content to the player that they need to interact with, obviously they need to have the same content on the server side too, because if you trying to run the same logic and the client has the new content and the server doesn't, the server would say, okay, now the client is lying to me, so you need to reload the state. So what we learned with LiveOps, if we could start over now, we would probably pay more attention to the tools that are necessary for creating a game that has a heavy live operations. You need to have good tools for notifications. So Azure Notification Hub is a good way to start off. Thinking about segmentation and how you're going to do that for the players is definitely something that should be done from day one. Cosmos DB has some great tools for that. So querying and indexing in almost real time is definitely a feature that Cosmos DB can provide. Campaign management. So how do you manage your campaigns? How do you manage all the content? You should figure out a clear way of presenting that and showing that, how campaigns are going to play out, what kind of content is going to be part of the campaign, what kind of notification is going to be part of the campaign, where is it available, how will that be segmented. And attribution is also a key thing when you're doing games on a mobile. What attribution means is that you want to be able to follow where did your players come from, so you can optimize your marketing. If you don't know where those players came from, for example, if you don't know which of the players came from Facebook advertisement or which of them came from Google advertisement, and then you can track how those players perform, you might be putting your money into the wrong campaign or wrong media. So what are we going to do next? What are our next big things that we're going to implement into our system? It sounds easy, only two things that we need to do. Firstly, we are going to move from cloud service into Service Fabric. That's a decision that we already made like a few months back, and it's work that we're working on. Service Fabric gives us a way more better fidelity, so we can back more stuff into one VM and reduce our costs. It's also way more easier to maintain, and we can more easily have rolling updates and more controlled updates. So we can introduce a small, an update that we can only introduce to a small amount of virtual machines, and then see how that plays out, and if necessary, we can roll back that update. And then another is truly globally distributed system. We're joking that we should actually change that into a planet scale system. It sounds more cool. But basically what that means is that now currently we're running all our services within one Azure region. So they're in one data center basically. What we want to do, we want to be able to distribute that system into multiple data centers in case of nuclear holocaust or just to shut out. But in order to do that, we need a system that can distribute that globally. And Cosmos DB is our way of going there. That guarantees us that we have the player information available within those regions that we want to support. So we can truly distribute that. That's it. That's how we done, and that's what we learned. Thank you.
Thank you.